In the last lecture, we were looking at the boundary layer analysis of transport from a heated surface in under forced convection, where convective effects are dominant compared to diffusive effects. So, only even when convection is dominant compared to diffusion, right, there is still a thin layer close to the surface where diffusion is important, because if you neglect diffusion altogether, then the equation just reduces to the velocity times dotted with the gradient of temperature is equal to 0. V dot grad T equal to 0 implies that there is no change in the temperature along the streamlines, along the velocity vector. So, therefore, the temperature at any location is the same as the temperature upstream before the fluid got heated. Okay. So, because there is no variation in the temperature along streamlines if V dot grad T equal to 0. That means that the temperature at any location is the same as the temperature at the upstream location before the heating started. Clearly, that does not satisfy the boundary condition at the wall, and we saw that we need to postulate the presence of a boundary layer close to the surface, where heat that is being diffusing perpendicular to the surface, heat that is diffusing from the surface perpendicular to the surface is getting swept rapidly downstream due to the strong convection, and therefore, the temperature change is restricted to a thin region close to the surface. That region is calculated from the condition that downstream convection and cross stream diffusion have to be of equal magnitude within this layer of thickness delta. In the limit as the Peclet number ratio of convection and diffusion becomes small, in the limit as the Peclet number, the ratio of convection and diffusion becomes large, the parameter delta becomes smaller and smaller in such a way that convection and diffusion are comparable within this layer. Okay. Note that we had defined the similarity variable as z by delta of x. Okay. The similarity variable as z by delta of x. Within this boundary layer, eta is order 1. Okay. Delta is a small parameter. Okay. Delta goes to 0 in the limit as the Peclet number goes to infinity. In fact, we had shown that for the case where we have flow from a flat surface, delta scales as Peclet number to the minus 1/3 power. Okay. Delta scales as goes as Peclet number to the minus 1/3 power. Okay, which means that the Nusselt number, which is the heat flux divided scaled by the diffusive scales, it is proportional to P e power minus 1/3. Okay. Is proportional to the Peclet number to the plus 1/3 power. Okay. So, the delta goes as P e power minus 1/3 and the Nusselt number goes as Peclet number to the plus 1/3 power. Okay. Therefore, delta decreases to 0 as P goes to infinity in such a way that cross stream diffusion and streamwise convection are comparable within the boundary layer for this problem. Okay. And based upon that, we had got a correlation for the Nusselt number. Okay. The correlation for the Nusselt number goes as the Peclet number to the 1/3 power. In that Peclet number, the parameter that is important is not the velocity itself, but rather the velocity gradient at the wall. Okay. The parameter that is important in the Peclet number is not the velocity itself, but the velocity gradient. The velocity, the average velocity, okay, is mostly due to the velocity near the center of the channel. Okay. Close to the wall, the velocity has to be small, because at the wall itself the velocity decreases to 0. Therefore, close to the wall, the velocity has to be a linear function of distance from the wall. Okay. Okay. So, therefore, it is this parameter Vs prime. So, the Peclet number is defined as, okay, Vs prime times L square by alpha. Okay. Vs prime times the length square or diameter square by alpha. Okay. And we saw how this analysis can be extended in a straightforward manner to the heat transfer in a pipe, provided the boundary layer thickness is much smaller than the radius of the pipe. the condition for the boundary layer thickness to be much smaller than the radius of the pipe we had derived here is that the length by diameter ratio has to be much smaller than the Peclet number. Okay, once the length by diameter ratio becomes comparable to the Peclet number, boundary layer thickness becomes comparable to the pipe diameter, and this analysis can no longer be used. Okay. So, under this condition that the boundary layer thickness is much smaller than the pipe diameter, we have derived a correlation for the heat transfer in a pipe flow, okay, which had exactly the same form as the correlation that is commonly used for the pipe flow, for a laminar flow in a pipe, except that the constant in that correlation is slightly different. Okay. Okay. So, next we were trying to analyze the flow in a stagnation point. Okay. T is equal to T infinity far from the surface, T is equal to Tw at the surface. The velocities, okay, the z velocity is towards the surface, so it is negative, x velocity is along the surface, so it is positive. Okay. And we had to substitute that into this conservation equation, okay, and solve for it, okay, using this approximation for the velocity close to the surface. Okay. So, therefore, the equation becomes k x z partial t star by partial x minus k z square by 2 partial t star by partial z is equal to alpha d square t star by dz square. Okay. Substitute eta is equal to z by delta of x. Okay. Partial t by partial z is equal t star by partial z is 1 by delta dt star by d eta. Okay. We had derived this before. Partial square t star by partial z square is equal to 1 by delta square d square t star by d eta square. And partial t star by partial x is equal to minus eta by delta d delta by dx dt star by d eta. These all we derived by differentiation by chain rule in the previous, okay, lecture. Okay. The same definitions apply here. Okay. So, therefore, I get k x z into minus eta by delta d delta by dx, okay, dt star by d eta, okay, minus k z square, okay, by 2, okay, 1 by delta dt star by d eta is equal to alpha by delta square t square t star by d eta square. Okay. And for x and for z I have to substitute eta times delta. Okay. So, this is delta eta, okay, and this one is delta eta the whole square. Multiply throughout by delta square by alpha, so that the right side becomes just d square t star by d eta square. Okay. On the left side I will have a negative sign throughout, k by alpha into x delta square d delta by dx plus delta cubed by 2, okay, whole into eta square dt star by d eta. Okay. that is the equation. Okay. So, I have x delta square d delta by dx, but delta cube plus delta cubed by 2 into eta square. Okay. So, you can easily verify this. I had a 1 over delta square here, and therefore, I get a this delta and delta will cancel out. Okay. Eta to the second power here, okay, on the left side on both the terms. Okay. And in this equation, the delta square and delta will cancel out. So, I will just get a delta cubed, okay, on the second term. Okay. This term has to be a constant in order to get a similarity solution. Okay. This term has to be a constant in order to get a similarity solution. It can be any constant. Okay. The constant can be set equal to 1. Okay. The solution for the temperature in terms of eta will depend on the constant. The solution for delta in terms of x will depend on the constant, but the solution for the temperature in terms of the original variables x and z will not depend on that constant. So, I can set that constant equal to 1 without loss of generality. Okay. So, I get, okay. So, in order to get a similarity solution, okay, in order to get a similarity solution, I require that k by alpha into x delta square d delta by dx plus delta cubed by 2, this has to be equal to 1. Okay. So, this is an inhomogeneous equation which has to be solved for delta. Okay. This is an inhomogeneous equation which has to be solved for delta. Once you solve that equation, the equation for eta just becomes minus eta square dt star by d eta is equal to d square t star by d eta square. Okay. So, that is the equation in terms of eta. Note that this equation is exactly the same as what we had for the flow past a flat plate. Okay. This equation is exactly the same. T star in terms of eta is exactly the same as what we had for a flat plate. Okay. The boundary conditions are the same. At eta equal to 0 or z is equal to 0, T star is equal to 1. Okay. T star is equal to 1 at the surface, eta is equal to 0, which is the same as z is equal to 0. T star is equal to 0 far above the surface, which corresponds to z going to infinity. Okay. So, the boundary conditions are the same, equation is the same, therefore, the solution is also the same. The only thing that is different is the solution for the boundary layer thickness in terms of the, okay, the variation of the boundary layer thickness with respect to x. This is an inhomogeneous equation. Okay. So, it consists of a general solution plus a particular solution. Okay. You can go through and expand it and express this in terms of the general solution plus a particular integral and then solve it. Okay. However, one thing you can see is that there is a particular solution which is that delta is equal to a constant. Okay. There is a particular solution that delta is equal to a constant. Okay. That particular solution is delta particular solution is equal to 2 alpha by k to the 1/3. Okay, that is the particular solution. Okay. Because if delta is a constant, d delta by dx is equal to 0, and this constant delta satisfies the equation identically. Okay. You can get the general integral. Okay. X by 3 d delta cubed by dx plus delta cubed by 2, this is equal to 0 is the homogeneous equation. Okay. Alternatively, d delta cubed by dx plus 3 delta cubed by 2x is equal to 0. Okay. And the integrating factor for this, okay, okay, and the integrating factor for this just turns out to be x power 3 by 2. Okay. So, the solution is delta cubed is equal to constant by x power 3 by 2 plus 1 by x power 3 by 2 integral 0 to x dx prime into x prime power 3 by 2 into 3 alpha by 2 x prime. Okay. If I substitute that into the equation, okay, the inhomogeneous term on the right side, okay, for this equation, okay, becomes, okay, 3 alpha by 2x. Okay. Okay. And this is final solution is xc by 3 plus 2 alpha by k. Okay. If you integrate this out, you will just get 2 alpha by k, because I have x power half, integral is x power 3 by 2, that cancels out with what you have in the denominator. Okay. So, and obviously this term has to be 0 if the boundary layer thickness has to be finite at x is equal to 0. Okay. So this gives us the boundary layer thickness, delta is equal to 2 alpha by k whole power 1/3. Okay. Note that for the flow past a flat plate, the boundary layer thickness increased as x power 1/3. Okay. The boundary layer thickness increased as x power 1/3 for the flow past a flat plate. Okay. In this case, it is a constant. Okay. In this case, the boundary layer thickness is a constant. It's independent of downstream distance. That is because the strength of convection, the velocity in the streamwise direction, which is the strength of the streamwise convection, actually increases proportional to x. Okay. The strength of streamwise convection increases proportional to x, due to which the boundary layer thickness is a constant. Okay. Okay. T in terms of eta, same solution as we had for the flow past a flat plate, because the equations are the same, the boundary conditions are the same. Okay. T star is equal to 1 minus 3 power 2 by 3 by gamma of 1/3 integral 0 to eta d eta prime e power minus eta prime cubed by 3. Okay. That is T star. Okay. The heat flux Qz is equal to minus k partial T by partial z at z is equal to 0. Okay. dt star by d eta at eta equal to 0 is the same as what we had for the flow past a flat plate. Okay. So minus, I should not have a delta x here. Into minus 3 power 2 by 3 by gamma of 1 by 3. Okay, that is the temperature derivative at eta equal to 0. This again we had solved when we solved the problem of flow past a flat plate. Okay. Okay. So this is the heat flux. In this case, the heat flux is a constant. For the flow past a flat plate, okay, for the flow past a flat plate, the boundary layer thickness increased as x power 1/3. Heat flux decreased proportional to x power minus 1/3, because it goes as the temperature difference by the boundary layer thickness. In this case, okay, the boundary layer thickness is a constant, and therefore the heat flux is a constant, which is also equal to the average value of the heat flux. Okay. So Q average is also equal to the same thing. Okay. and this is approximately 1.62. Okay. Sorry, if you do the calculation of all these constants, you will get approximately 0.62 k into T w minus T infinity by alpha by k power 1/3. This k in the denominator is the parameter in the velocity profile. Okay. And the Nusselt number can be written as qz q average by k into T w minus T infinity by L, okay, which is 0.62 into k L cubed by alpha whole power 1/3. Okay. So, in this case the boundary layer thickness is a constant, so the average heat flux is equal to the local heat flux. Okay. Also note that the velocity goes as k times x times z. Velocity is length per unit time. Therefore, k has dimensions of 1 over length, 1 over time. Okay. K has dimensions of 1 over length and 1 over time. Okay. So, k times L cubed has dimensions of length square per time, and therefore, this is effectively a dimensionless group. A Peclet number based upon the parameter k in the stagnation point flow and the length and the total length. Okay. So, this is the expression for the stagnation, the boundary layer thickness in a stagnation point flow. Okay. Similar problem, okay, note that the temperature field expressed in terms of the variable eta, the equation for that was exactly the same for the flat plate stagnation point flow. The expression for delta in terms of x was changing. Okay. So, once you got the temperature field in terms of eta, it is the same for any flow in which there is a no slip condition at the surface. The heat flux in the boundary layer thickness in terms of x is changing. Therefore, the heat flux at the surface is dt by d eta times 1 over delta, okay, into a factor of the thermal conductivity and temperature difference. That 1 over delta is the only one that depends upon the downstream distance and on the configuration of the flow. Okay. So, in that sense, the temperature field, scale temperature field in terms of the similarity variable is exactly the same for many different kinds of flows. Okay. In fact, we will see it is the same for any flow so long as the no slip condition is applied at the surface. Let us consider a slightly more complicated example, okay, that is diffusion from a solid particle. Okay. I have a solid particle of radius r, okay, and there is a free stream velocity far upstream. And far upstream the temperature is T infinity. The temperature at the surface of the particle is T naught. Okay. The temperature at the surface of the particle is T naught. Okay. And as the flow goes around the particle, I want to find out what is the rate of heat transfer, rate of diffusion from the particle, okay, of thermal diffusion from the particle. Okay. In a spherical coordinate system in which the z axis is in the direction of the flow. Okay. So, the z axis in the direction of flow, okay, at any location r, this the radial vector is r, this is theta, and the angle around is phi. Okay. You have the flow that is incident on the particle at this what is called the stagnation point. Okay, this is an upstream stagnation point, okay, and there is similarly a downstream stagnation point here. Okay. Theta is equal to pi in this case and theta is equal to 0. Theta is equal to 0 at the upstream stagnation point and theta is equal to pi at the downstream stagnation point. The equation V dot grad T, Vr partial T star. Okay, so I will define T star straight away. T star is equal to T minus T infinity by T naught minus T infinity. Okay. Boundary conditions are T star is equal to 0 for r going to infinity, T star is equal to 1 at r is equal to capital R. Okay, so those are the boundary conditions. Del square T equal to 0 is the conservation equation. Sorry, V dot grad T is equal to d del square T is the conservation equation. Okay. Partial T star by partial eta. Note that the flow, the streamwise direction is along the streamlines. Okay, for the flow, the streamwise direction is along the streamlines. Okay, so along the particle surface, the streamwise direction is the theta direction. Okay, along the surface of the particle, the streamwise direction is along the surface. The cross stream direction is perpendicular to the surface. Okay, so the cross stream direction is the radial direction. The streamwise direction is the theta direction along the surface. In boundary layer theory, the diffusion along the streamwise direction is neglected. Diffusion is primarily along the cross stream direction. Okay, the diffusion along the streamwise direction is neglected. Diffusion is primarily along the cross stream direction. Okay. Therefore, we can neglect this cross stream diffusion in comparison to the streamwise diffusion. Sorry, we can neglect this streamwise diffusion in the theta direction. Okay, we can neglect the streamwise diffusion in the theta direction in comparison to the diffusion in the cross stream or the r direction. Okay, we can neglect the diffusion in the streamwise direction in comparison to the diffusion in the cross stream direction. Okay. Now, if we look at we would expect in the limit of high Peclet number for diffusion to be limited to a thin boundary layer close to the surface. Okay, we would expect diffusion to be limited to within a thin region close to the surface. Within that region, okay, we can define a scaled coordinate. So, this is the surface, r is equal to r. Okay. So, away from the surface, you would expect the diffusion to be limited to a thin boundary layer delta. That delta has to be a function of the streamwise direction. Okay. Streamwise direction in this case is theta. Okay. So, we expect delta to be some function of theta. Okay. The velocity components for the velocity field in this direction are defined for us. Okay. So, the velocity components are Vr is equal to minus V free stream cos theta into 1 minus 3 r by 2 r plus r cubed by 2 r cubed. Okay. And V theta is equal to V free stream sin theta into 1 minus 3 r by 4 r minus r cubed by 4 r cubed. Okay. So, that is the velocity that is defined for us. Okay. We have to substitute that into the diffusion equation and then try to solve it using the boundary layer approximation. That how do we apply the boundary layer approximation for this rather complicated velocity profile? Previously we considered relatively simple velocity profiles, a linear profile close to the wall, okay? And therefore we were able to get solutions for the velocity. How do we do the same thing for this rather complicated velocity profile in a manner similar to what we did for the flow past a flat plate and the stagnation point flow? Approximations for the velocities close to the surface have to be used in this case. Okay. How do we get those approximations? That I will continue in the next lecture. I will see you then.